Hi again. This is a look at the second part of the quantum mechanical model of the atom. Let's take a look at the electron configuration then of ions. I've started here with the energy level diagram. And the first thing I'll look at are anions, or substances that have negative charges. For my example, I'll take a look at sulfur. Sulfur normally possesses 16 electrons. For the ion, I'm going to take a look at sulfur with a 2- charge, where it has 2 additional electrons. Let's begin with sulfur in its neutral state. A sulfur atom possesses 16 electrons, and beginning at the lowest energy level and moving up, this would be its particular electron configuration, finishing with a second electron being placed in the first p orbital. I now have to add 2 electrons to this to make it a -2 ion. Those I've indicated here in red. And now its configuration would be as follows. So to simply arrive at an anion, one simply continues to fill the orbitals in the same sequence that one would do for a normal atom. And you add the number of electrons equal to the charge. To get a cation, or a positively charged species, we have to remove electrons, and they're removed from the energy level that has the highest principal quantum number. I'll take a look at 2 examples of this. Let's begin with a simple example, the potassium. Potassium normally has 19 electrons, and they would find themselves in the following locations. The highest principal quantum number here is 4, so I would remove that electron from the 4s orbital, leaving the following configuration. Let's look at a little bit more complex example now. Iron possesses 26 electrons. They would have the following configuration. Now, to turn this into an ion, I have to approach the highest principal quantum number, which isn't the 3d, but the 4s. The first 2 electrons would be removed from the 4s, and then the next electron I need to remove, that would come from the 3d orbital. And now I would have the following configuration. So be careful not to remove electrons from necessarily the highest energy level, but from the highest energy level with the highest quantum number. Let's look at the connection between the quantum mechanical model and our periodic table. Elements that are in the same column in the periodic table have similar valence shell electron configurations. And I'll explain what valence shell electrons mean when we take a look at a few examples. I'm going to consider boron, aluminum, and gallium, all located in the same column in the periodic table. Boron has 5 electrons. The first ones would be placed in the 1s orbital, then the 2s orbital, and the 5th and final electron in the 2p orbital. So it would have the following electron configuration. Valence electrons are those with the highest principal quantum number, which in this case is 2. So I've circled here what would be considered the valence electrons of boron. Let's go to aluminum now with 13 electrons. I would continue to move on from boron by adding 5 electrons to fill up the 2p, then I would move to the 3s, and then the 3p. And so its configuration would be as follows. And now the highest principal quantum number here is 3, so those would be its valence electrons. Now to move on to the element gallium, I would begin at aluminum, add 5 electrons to the 3p, then move to the 4s with 2 more, add 10 more to the 3d, and I would finish up at 4p with 1 electron. And it would have the following configuration. The highest principal quantum number here is 4, so here I've circled its valence electrons. One thing that you'll notice is all of these elements have a similar valence shell electron configuration, S2P1. Now let's take a little bit of a look at the dimensions in our periodic table. The first thing that you'll notice is over by boron moving through to neon that it's 6 elements wide. The reason that happens is the p orbit can hold 6 electrons. Over on this side of the table, that block in the periodic table is 2 elements wide. That's because the s orbital can hold 2 electrons. The transition metals located here in the middle are 10 elements wide. That's because the d orbital can hold 10 electrons. And the 2 rows that are pulled out at the bottom of our periodic table, they can both hold 14 elements wide, and that's because the f orbitals, 7 of them, can hold a total of 14 electrons. Let's look at this a little bit more closely. As I mentioned here, this is the p block. And what I begin with is P1, and as I move across towards to neon, I eventually fill it up with p6, sequentially. Similarly, the d block begins at 3d1 and moves across to 3d10. Now, the reason it starts at the third energy level goes back to our orbital filling sequence. We don't get d orbitals until we reach the third energy level. And likewise, down below in our f block, it doesn't begin filling until we reach the fourth energy level. Hence, it moves from 4f1 across to 4f14. And of course, our first two rows, or columns in the periodic table, are the s block, filling up s1 and s2. We can abbreviate the writing of electron configurations by use of noble gases. So for my example, I'm going to take a look at gallium and look at a shorter way of writing out its configuration that uses noble gases. The noble gases are located in the far right column of the periodic table. Now I'm going to ignore helium and begin with neon. Neon, with its 10 electrons, would finish 2p6 because it's in the sixth column on the p block. Argon would finish 3p6, krypton 4p6, and xenon 5p6. I'm going to go over here to my orbital filling sequence now and replace 2p, 3p, 4p with their corresponding noble gas. Now, if I want to come up with the electron configuration for gallium, the first thing I do is I move from gallium and I move backwards to the nearest noble gas, which in this case would be argon. Argon possesses 18 electrons. That essentially means I can replace these 18 electrons with the symbol argon in square brackets. With 18 electrons now placed, I just need to place another 13 to arrive at 31. So the next place I would go after argon, according to the orbital filling sequence, would be 4s, where I would put 2 electrons. Then I would place 10 of them in the 3d orbit, and my remaining electron that I need in the 4p1 orbit. So again, starting at a noble gas, the nearest noble gas that is back from its location, I can quickly arrive at something's electron configuration. Be careful when you read a question whether it asks for the full electron configuration or abbreviated electron configuration. Now, let's take a look at 3 other elements: vanadium, chromium, manganese, and then copper. Let's start with vanadium's electron configuration. With 23 electrons, I back up to the nearest noble gas, which in this case is argon. From there, with 18 electrons, argon, I need 5 more. The first place I place them is the 4s orbital, 2 of them there, and finally the 3d orbital, which arrives at 23 electrons. I'm now going to do the next 2 elements. Chromium would have 1 more electron in its d orbit, and similarly manganese. Now, something special happens with the element chromium. It turns out that from its properties it appears that the 4s orbit has only 1 electron in it, and 1 has been promoted to the d4 orbit to make it d5. So chromium's actual experimental electron configuration shows that it finishes 4s1, 3d5. Something similarly happens with the element copper, which we would expect from its location to be 4s2, 3d9. Again, one of the s electrons is promoted to fill up the d orbit. Now, the reason this happens is because half-filled s and half-filled d orbitals tend to be more stable, and by promoting an electron, we can essentially achieve that. In the case of chromium, promoting the electron allows us to have 2 half-filled orbits, which are more stable than a full and a non-filled orbit. Similarly, argon, by promoting, copper, by promoting that electron, we essentially have a half-filled s orbit and a full d orbit, which again is a more stable configuration. So that ends our look at the atomic theories, finishing with our quantum mechanical model of the atom. Again, comments are always welcome, and don't hesitate to post any questions.